Let's talk about force statics. What we want to do here is, go back to an example that we had solved earlier, where we were talking about what joint torques need to be applied to apply a specific force against a wall, right? A similar scenario, what joint torques need to be applied to apply a certain force on the environment. How do we calculate that relationship? Of course, we derived this for the specific case, but let's go back to a more general situation. And here we will find that we can take advantage of the Jacobian again. And many of you would already have seen this pattern that force and velocity tends to be inversely proportional or inversely related in some way or the other. You see that in gearboxes, if you get higher force or higher torques but lower velocity, and if you have higher speed or higher velocity, then you get lower torque. You also see it in motor characteristics. Sometimes you see it in many places, right? So we will see a somewhat similar relationship here. But first, let's go back to our Jacobian velocity kinematics equation. But here now I'm going to write this in a different format. I'm going to write this as velocity, remember, was just the velocity of the end effector. So in this case, the coordinates of p, x, y, the derivative of that was velocity. So now I'm going to write this as, this is also true in the differential form, where I can write delta, sorry, not delta q, but delta p. Delta p, which is the change in the coordinate of p, is equal to jv times delta q, which is the change at the joints. I can further then apply principle of virtual work. Now, principle of virtual work, some of you might have seen already, and those of you who have seen, I wouldn't be surprised if you are a little confused about it. I still sometimes get confused about principle of virtual work. But basically the idea is, even if something is not moving, first you imagine if it moved through some infinitesimal allowable displacements, then what would the virtual work done be? And then for a static equilibrium case, you equate that virtual work to be equal to 0 and then solve for the variables, and that helps you establish a relationship. Anyway, in our case, it's relatively straightforward. We don't need to get into the principle of virtual work. But basically, in our case, the virtual work will consist of two things. One, there are external torques being applied on the robot because a motor is applying a torque on the robot, right? So you would have a work done due to the torques. So you have a torque times delta q, and since this is work done externally, work done on the robot, I would treat this as a negative work, and the other part would be F times delta P, where in this case I'm showing F as the reaction force from the wall, but really the way it all started is the robot is applying a force F on the wall. So it's a force applied by the robot on the environment. So this is a positive work because robot is pushing against the environment, and this is negative work because torque is being applied on the robot, right? So this, I would then use delta P is equal to JV times delta Q over here, and then I could write this as F JV minus tau. By the way, I would have to make this is a scalar and these are all vectors, so I would have to do a transpose. I had forgotten to put that earlier. So I would get an F transpose JV minus tau transpose multiplied by delta Q, right? So I substitute delta P equals JV times delta Q over here and then reorganize it to get this. And we know for static equilibrium, the virtual work done is 0, which means I would get F transpose JV is equal to tau transpose, or in other words, if I take the transpose of the whole equation, I get the joint torques that I need to apply to in order for the robot to apply a force F on the environment would be JV transpose times F. That's it. It's as simple as this. So as we can see, we still get the Jacobian relating the forces and the torques, except that now it's a transpose. In our velocity kinematics, it was just JV, but in the force torque relationship, it's JV transpose. But given a desired force that I want the robot to push against the environment, I take that desired force multiplied by JV transpose, and I know what torques I need to apply at the individual joints. These are both vectors, and this is a 3 by n matrix. Transpose of that will be n by 3 matrix. Simple.